Let's go ahead and get started. People can sort of wander in. Are we all ready to go? Good, okay. So before we start, so today we're going to finish up talking about free text analysis, and then actually next time we're going to use the overflow lecture to talk about the spatial data and GIS systems. So a quick sort of note. I've been thinking about this a little while. So a few people have mentioned to me that there's sort of this issue with the, sorry, everyone, quiet. This will be important. You'll want to hear this, I'm pretty sure. All right, so there's been an issue with the office hours, I think, and it's not really an issue with it. I think it's sort of the nature of office hours as they are, is that it's kind of hard to ask more conceptual or high-level questions in the office hours, right? A lot of people going to the office hours are sort of, asking, what's the problem with, they're running into a problem with their code and they want to know sort of how to address that. And so it's kind of hard to get your more sort of conceptual, high-level questions about the assignments answered in those office hours. It's not a good time for that. And I think then, when you do get time, it's sort of a short response because the TAs, the lines out to office hours are very long, and so they have a short time to deal with anyone sort of asking, maybe more high-level, how does this kind of work questions. And I think that's a pretty valid point, and I've had a couple emails about that. And so starting this week, I'm going to be holding kind of a more high-level office hours about the homeworks, but from a high-level perspective. It'll be this Friday, and I'm not sure what time or place yet, because I have to figure out what rooms are available, because I want to have a reasonably large room for those that want to come. But the idea is that at the beginning, we're actually going to vote on the topics that we'll go over, and it'll be a more sort of, well, I won't look at any code. I'm not going to debug any code. If the question's about, how to use some function, I won't be covering that. That really is actually what the office hours that we have are good for. What I will be doing, though, is kind of going over conceptual questions you may have about the nature of the assignments. So if you I think a lot of people are running, and we tried to do this with Piazza recently, but a lot of people are running into issues with the conceptual issues about what we're really asking with that, running with the rolling sums and the rolling averages, right? So things like that, those are good things to ask there, and we can kind of clarify what we mean by the questions and how you might go about approaching them from a high-level logical standpoint. So that's the goal of this. I'll start it weekly, and I think there'll be, if no one shows up, I'll stop, but I can't imagine that would happen. So we'll see how it goes. I'll intend to hold it at least for the next several weeks whenever there's homework out at the current time. And even actually when the tutorial is out, we'll have that as well. Also, actually, I didn't put it here, but just a reminder that the tutorial will be released. The information about it will be, as mentioned on the website, the tutorial will be released next Wednesday along with the next homework. So in addition to the next homework, you'll also have some information about the tutorial and what that will involve. Okay, any questions on this? Okay, sounds good. Okay, so when we stopped last time, we were talking about cosine similarity. So you remember that we're talking about free text, right? And we were talking about summarizing documents by these TF-IDF vectors. And essentially these encode, the terms that occur in that document, also where the terms are weighted by some factor depending on it's actually the log of the inverse frequency of that word. And that forms the TF-IDF vectors. Now when you do that, a common thing you want to do in documents is sort of measure how similar two documents are, or maybe find the most similar document to some given new document. And a common way of doing this is with a method called cosine similarity. So this is sounds like a fancy thing, but really it's just a fancy name for a normalized inner product between the two vectors. So if I have two vectors, x and y, that define TF-IDF vectors, I first normalize them. That's sort of the division by the norm of x, the norm of y. Remember, the norm is the square root of the sum of the values of the vectors squared. And then I take the inner product of those two vectors. So you can write it like this, where you first take the inner product and divide by them, or you can write it in terms of first normalizing each vector and then taking the inner product of those two vectors. And this is a number between 0 and 1. Higher numbers indicate more similar, lower numbers indicate less similar. And I didn't do this last time, but I actually just wanted to emphasize that this is actually this is essentially the same thing as 1 minus the squared distance between the two vectors. And you can see that really easily, actually. So I'll just do a little bit of very basic linear algebra here. But if I have a vector x, which is the normalized version, oh, there we go. Normalized version of x, and we have y tilde, which is the normalized version of y. Right, so those will both have norm 1, actually, when you do that. Then the cosine similarity between x and y, which is just equal to x tilde transpose y tilde. This is related to the distance between these two vectors. So I can also compute, separate from this is sort of point 1. Point 2 is another sort of natural way to measure the difference between these two things, would be the Euclidean distance between them. So I can also compute, I'm going to put a 1/2 here for reasons I'll see in a second. X tilde minus y tilde squared. And remember here, for some vector x, this thing is just equal to the sum over all elements in the vector of xi squared. Okay, this is just notation. So this thing here, I'm going to do some linear algebra now, but very simple linear algebra. This is going to be equal. This is, by the way, also equals the inner product of x with itself. So x minus y transpose x tilde minus y tilde. I'm just going to distribute this out now. This is now x transpose x tilde minus 2 x tilde transpose y. Sorry, there's 1/2 in front of this. 1/2 plus y tilde transpose y. This term here is equal to 1. This term here is equal to 1. And this term here is just the cosine similarity between x and y. So this whole thing is just equal to minus the cosine similarity between x and y. So this is just sort of trivial math here, but the cosine similarity is just sort of a fancy name for also 1 minus the difference in Euclidean space of a normalized version of those vectors. I guess 1 minus the distance of squared in Euclidean space between those two vectors. So that hopefully helps you understand why that's maybe a good metric, right? So for this thing will be 0 when the vectors are the same, and 1 when they're as far apart as it can be. And that's sort of the opposite. The cosine similarity will be 0 if they're as far apart as they can be, and 1 otherwise. Okay. Everyone good with that? Okay. All right. So as a quick example, let me go back to this. Here is the cosine similarity matrix of the TF-IDF vectors for these 3 documents. So these are our documents we're considering before. I sort of, computed the TF-IDF for all of them, TF-IDF vectors for all of them. You remember that was a few slides ago. And I just take I normalize those vectors, take the inner products, and we get these terms here. And so what these say is that in some sense, the second 2 sentences are more similar to each other than either is to the first one, right? Because these have a higher cosine similarity than the other ones. And you can sort of see why. They both had the phrase bag of words, amongst others, right? That's probably actually the main thing. It's actually probably the only thing that they really have in common. But that's already 3 words that they have in common. And so that's, a reasonably high similarity. Though, notice that none of these things are that similar, right? These are not that similar. Probably because things like of will not count at all, because we downweight that word entirely. And, only what's left is sort of the unique words to each thing. That's the whole point of TF-IDF. And so you have smaller than, of course, inner products of similar words between 2 vectors. Okay, so this will take us to the first poll, actually the only poll of today. We didn't get to it last time, so we'll get to it now. And the question is, what would you expect to happen to the cosine similarity if you use the normal term frequency instead of the TF-IDF vectors? Right? So instead of weighting all the term frequencies by their inverse document, the log of the inverse document frequency, you just directly take inner products in the term frequency vectors. So that'll be the question. Let me open up Piazza, the Piazza poll. Okay. Yeah.
Are you asking about like the general case or those three sentences that you're showing?
You could do either, actually. But what should happen? I mean, this is sort of in expectation. What do you expect to happen? And what you expect to happen probably will happen there too. We'll do maybe one more minute. All right, 15 more seconds. All right, and I'm closing it now. Okay, so let's see what people said. All right, so oops, close that. Okay, so most people said cousin similarity between objects would go up. Does someone want to offer an explanation of why they think that's the case? Yeah. So that's exactly right. So what will happen is that in general the average similarity will go up, and the reason why is that the terms that occur very frequently are those that are downweighted by the inverse document frequency. So you have a term that occurs everywhere, even if you don't explicitly remove stop words, right? If you don't remove them explicitly, if you have a term like the of term that occurred everywhere, it got a weight of 0 because it was the log of 1, and so you downweight it to 0. And so what's going to happen is that you're going to have a lot more words that occur in all the documents that are not downweighted and therefore factor into the inner product between them, right? And so that's going to, in general, sort of raise. Certainly in this case, it does, and in general also, it will raise the number of, or raise the average constant similarity between all the documents. It won't necessarily actually give you anything more informative. Probably actually just the opposite. It would be less informative because, all of a sudden the fact that every document contains of is gonna matter. And if one document that happens not to contain of, that would be a big, that would downgrade similarity a lot. And so it doesn't give you anything more informative, but the actual numerical values of cosine similarity would tend to go up in that situation. Okay, so let's keep going. Where's my cursor? I feel like it's there somewhere. It's just not. All right, we'll do that. Okay, so moving on from that. All right, so this is actually, and I said this last time. I picked a bad day to say that a bad week to try to catch back up with the notes because I ended up changing a fair amount of this lecture, and also the next one is a new lecture, so bear with me again a little bit, I guess. But these notes should be up pretty soon. The next thing I want to talk about are word embeddings, and in particular the word2vec word embedding tool. And actually, I'm using the word word2vec here. There are actually a lot of similar algorithms these days that are sort of well known that all do the similar thing of word embedding. So the basic idea here is that you can think of individual words in a term frequency models as kind of being vectors in a high dimensional space, right? So the word Pittsburgh, right, essentially corresponds to a vector, which is called these are sometimes called one-hot vectors, where essentially you have a component for every possible word in your vocabulary. So here the number of words is the total number of unique words across all the documents. But you have your total vocabulary, and then the word Pittsburgh in some sense corresponds to, I'm going to use the notation E subscript Pittsburgh. That's not that standard, just E is often used as a basis vector, basically a vector with 1, 1, and zeros everywhere else. So I'm going to use this vector E. And that is just a vector that has, a 1 in the location corresponding to Pittsburgh and a 0 everywhere else. It doesn't have to be sorted even, but I'm sorting it there. So, if you have a corpus with the word pitted, Pittsburgh, and pivot all together, then this, that word is Pittsburgh. It's not pitted and it's not pivot. And then, hopefully, because it's kind of obvious, but if I now want to compute the term frequency vector for a document, I just sum up the word vectors for all the different words. Okay, so that's just notational. I really hope that point's not confusing. It's just a different way of sort of writing what I already did. That the term frequency vector is just going to be the count of the number of words that occur, and so you can think of that as adding up a bunch of vectors. A bunch of these one-hot vectors. Okay, now the problem with this approach is that these vectors don't really have any notion of distances between them, right? So let's take two vectors, one for Pittsburgh and one for Boston. Actually, the thing there is not 1, it's actually square root 2, so I should say like 1/2 of that thing squared. Anyway, let me change that. Just do this really fast. Just to be accurate here. Okay, that's better. Of course, each has a 1 in one location, a 1 in the other location for the other word, and when you subtract them, then you just get a, right? So sheet here, E Pittsburgh minus E Boston would just equal some vector that has a -1 in the Boston column, zeros everywhere else, and then a 1 in the Pittsburgh column. Sorry, Pittsburgh row. So this is this row here is the Boston row. This row here is the Pittsburgh row. So when I subtract, so when I take the norm of this, the norm squared, that's just going to be equal to 2, no matter what. And so what this means is that the distance, in some sense, has no real meaning. It's either 2 or it's 0. If they're the same word, it's 0. If they're different words, it's 2. There's no sort of notion of actual distances between words in these word vectors. Right? And that somehow doesn't seem right? Because somehow some words seem more related than other words. Right? So suppose I have this next corpus here, which says this has 3 sentences. The first says Pittsburgh has some excellent new restaurants. The second one says Boston is a city with great cuisine. And the third one says Postgres is a relational database management system. Now in TF-IDF vectors, assuming I don't remove any stop words here, these two would actually be the most similar because they both have is and a in the sentences, and these other two have no overlap in words there, right? So the similarity between these two would be 0, and this one would be small because the mostly different words, but something, non-zero, right? So the problem here is that under these similarities, then there's no notion that these two are really kind of talking about the same thing, because all our words are just either completely different or exactly the same. Right? There's no notion of sort of similarity amongst words. Now, the answer to this, in some sense, or one answer to this problem, is given by what are called word embeddings. So a word embedding is another way to represent words as vectors. And we're going to do that by taking words and representing them as vectors in some space Rk, where k is some number. It actually does not have to be the number of total words in a document. It's usually, or total vocabulary of words. In fact, it's usually less than that. It's usually like people pick 300 for some reason. I'm not sure why that's a common number to use for the dimension of k there. But the idea is we want to take all the words in some large corpus, all the unique words in some large corpus, and embed them all into some k-dimensional space, such that words that are similar appear close together in that space. So they have a small distance between each other. So maybe you take these words and you would have Boston and Pittsburgh close together, but then database would be far from those. Right? And that's the idea of word embeddings. Now, there are lots of ways to create such word embeddings, but one that has taken over a huge amount of popularity recently is these models that go generally by the name of word2vec, even though word2vec is actually only one of many possible models that people can actually use. This is actually a new topic for this time in the course. I try to add the things that are sort of becoming standard tools, and this definitely in the last few years has become a standard tool in analyzing free text. It was already around certainly a few years ago, but not that old. It's only 5 or so years old. Actually, I think 2014 was the paper. The general idea of word embedding is, of course, a lot older, but word2vec is actually pretty recent. And it's really ignited a lot of interest in this area. So all of a sudden, these things have become really a standard tool for how you go about analyzing free text. Now again, we're still in the bag of words model, right? We're still saying we're just going to take all the words in a document and just consider vectors for each individual word. But now somehow we had this notion of some words being more similar than other words, right? So we have this sort of additional power to our model. Now, unfortunately, we don't really have the tools yet to talk about how you build the word2vec embeddings. Notice actually it's also notational. I am going to, so in general, I'm going to use this E Pittsburgh to refer, this is some vector in the number of unique words, to be the one hot vector. And I'm going to call W Pittsburgh in RK to be the word embedding. So I'll try to be consistent there. I'll refer to W as the word embedding and E as the one hot encoding of that word, just notationally. Okay, so how do you construct these word embeddings? Again, we don't really have the tools to do that yet. We will cover this a little bit when we talk about. We'll cover similar things when we talk about machine learning. If we have a lot of time, we'll come back to these kind of models. They're actually quite simple. What they do is they take the actual. There's actually a few ways of doing it. One of the most common is called a skipgram model. And what it does is it actually tries to, for an entire sort of corpus, you look at words like Pittsburgh, and you look at words that occur around Pittsburgh on both sides of it. So you remove maybe stop words, but cities, U.S., Boston, building, that kind of stuff. And this is going to sound strange, but what you try to do is you try to predict the context around the word from the word itself. Okay, so I'm going to try to actually predict all these things, the actual one-hot vectors of all these things, from Pittsburgh, the one-hot vector of Pittsburgh. Now, of course, you can't actually do that. You can't succeed at that task, right? This is not a task that is possible. But in trying to do as well as you can to model the probability of the different words, given Pittsburgh being kind of the center word, you can kind of construct these vectors. And in particular, what you typically do is you sort of have a projection, basically a matrix here applied to your one hot vector that shrinks it down into this size. And then you try to make that ensure that that's sort of similar to all these other ones, or can kind of predict these other one hot vectors. Okay? So again, we don't have the sort of the tools yet to actually define what I mean by that. We will get those when we talk about machine learning, but we don't really have that yet. But for the sake of this, just know that what they're trying to do is they're basically trying to predict nearby words from a given word, going through this kind of projection step, or kind of sub-step of representing this as a vector instead of a general vector instead of just a one hot vector. Okay? So that's how word-to-vec models work. But again, that's how they work very briefly. But what's actually nice about these from a data science perspective is that you don't really have to worry about training these models. I mean, there is code out there that will train them, but there are also a lot of pre-trained models that kind of exist out there. In particular, Google and their original word-to-vec model, or the original paper, they took about a corpus of about 100 billion words from Google News feeds. And there was about 3 million unique words in this feed. And they just went ahead and pre-computed word vectors on this entire set of 3 million words. So all of this is this is a lookup table from 3 million words to a 300-dimensional vector in this case that is their word vector. And it just because they trained it on a very large corpus, it ends up being pretty useful for a lot of different tasks, right? Unless your task is really specialized, like you have some, comment system where there's some vocabulary that doesn't occur in any news articles, chances are your words appear somewhere in those 100 billion words, and so, or really 3 million unique words, and so you actually have some notion about the words that will occur in your documents and how they relate to other words. And so the original one is here. If you want to sort of get some a little bit more manageable versions, the one thing about the entire data set here is it's like uncompressed is something like 4 gigabytes. And so when you load it into memory, you have to have at least about 16 gigs of RAM, or it really won't. It'll just run out of memory on your machine. So it's not super manageable on laptops, for example. But if you want a little bit more manageable ones, there's some smaller ones here that have much fewer words. They're trained on like Wikipedia, these ones. They're much fewer words, but they still work pretty well, right? And so for common words, they're still going to work. Okay, so now what do these actually get you in some sense? So it's actually pretty... I'm actually personally kind of always astounded by what some of these things can actually do. So there's 2 kind of common things you might do with these words. And we'll talk actually, and the third one would be you kind of use them in kind of a document vector sense, which we'll get to in a second. But there's 2 kind of immediate things you can do with these. The first one is just look up closest words to other words to get some sense of how words relate to each other. So if I take the word Pittsburgh and look at the vector embedding of Pittsburgh. Again, that's just a hard-coded 3-dimensional vector once you've trained the system, right? Once if you download Google's 3 million word-to-vec database, it's just one of the words is Pittsburgh, and you can just look up what are the other similar words. And the most similar words are all cities kind of in the Northeast and Midwest, right? It's Chicago, Cincinnati, Boston, and Detroit are the closest words to Pittsburgh. Again, only training it to sort of predict context around the word given that. But what happens is, people frequently say things like eastern cities like Boston or eastern cities like Pittsburgh, right? And so naturally these things will sort of tend towards similar vectors. What's really kind of amazing here is actually you can also do things like reasoning by analogy. So the idea here is that this encodes, these vector spaces encode more than just sort of similarities between, or encode more than just sort of similarities between existing points. They also encode kind of relationships between different words. All right, so the figure's there, but I actually want to draw this again as well to kind of emphasize it. Because this is not trained. They're not trained to do this. This emerges naturally, which is kind of this amazing phenomenon. So say we have some points here. So here we have a point of the word embedding of Boston. We believe this will be similar to the word embedding of Pittsburgh. And similarly, we probably think that the word embedding of Massachusetts is going to be similar to the word embedding of Pennsylvania. But what's really impressive here is that if I look at this vector from Massachusetts to Boston, and that vector, by the way, is just Boston minus Massachusetts, of course, right? That's the direction from Massachusetts to Boston. That somehow encodes something like, big cities in this state, right? So a state and large cities in the state. So this relationship here, this vector, somehow encodes something like, a big city in the state. And so if I take, W Boston minus W Massachusetts, that's this vector, right? And if I then add it to W of Pennsylvania, and I look up the closest words to this, you actually get Pittsburgh as the closest word. And that is totally wild, right? There's no reason why that should ever happen, just from how it's trained. I mean, we're not training it to learn to reason by analogy and things like this, but these patterns kind of naturally emerge out of training a language or trying to predict sort of language features on a model of this size. So it's really kind of amazing. So again, if I go and look at the closest words to Boston minus Massachusetts plus Pennsylvania, actually, to be fair, the closest word to all that is just Boston. Because these are very close together, right? Whenever this term is sort of small, whenever you take a term and try something small, it's still closest to Boston. But if you ignore Boston, which typically you do because it's one of the words in this relationship, the closest remaining thing is Pittsburgh after that, and followed by Philadelphia. Then you have Chicago and Denver, I guess, which are just cities, but it's still pretty impressive. Because Philadelphia, by the way, was not one of the closest cities to Pittsburgh. But somehow it knew, because it's Pennsylvania we're talking about now, that it's now Philadelphia is one of the cities there. It's really a sort of amazing stuff. Okay, so the thing that I do want to emphasize, though, is that the reason why it's such a powerful tool in data science is that because you have these pre-trained models, you can just take your free text and essentially convert it to vector representations that tell you about similarities between different vectors, right? And different words in your corpus. And you can sort of take things like we were doing with term frequencies, but do them now extending them to the case of sort of understanding the meaning of words, not just their presence or absence. And in fact, sort of the obvious thing to do here is use like a bag of words, extend the bag of words model to kind of a bag of word vectors. So instead of just adding up the indicators, the one-hot functions in my term frequencies, I'm going to create a vector of my document by adding up the word embeddings for each word in that document. Okay? And this, in a real sense, does capture the meaning of the words much better than just taking the sort of the raw frequencies. So if I run the same example here, so now these three sentences here, in the TF-IDF, the first and second have a 0 similarity because there's no overlapping words there. In the word embedding sense, first, two things to note. First of all, they're all pretty similar looking. That's a fact. That's a effect of a bunch of things, but when you have two, I am still adding things like the word embeddings of is and a. So these actually get quite a bump, just having two identical words in their embeddings. And the embeddings typically, there's a lot of words that have near like a 0.4 or 0.3 similarity. So when you add things up, you get you get much higher similarities than you typically would with TF-IDF, just because these vectors are sort of they're dense, they're not sparse, and so you typically get some amount of overlap. Okay, but the important thing here is that actually now the highest similarity two sentences are in fact these first two sentences, despite the fact that they don't share any words. Okay, so they share no words, but they're talking about similar things. They're talking about cities, they're talking about food, and so they actually can kind of overcome the fact that they have no words in common and actually be the highest have the highest similarity between pairs of documents. Question over there. Why are the first and the third still similar? Yeah, so it's definitely the lowest of all the similarities, right? So it's 7, which, I mean, the way you should think of that is that you're basically resetting the baseline for these things. So you shouldn't think of them as being 0, because when you have vectors that are sort of all dense, embedded in some space, chances are the differences will not have norm 0. They won't be essentially orthogonal vectors is what that would boil down to. So a lot of generic words, some, new, is, a. These are all kind of generic words that all kind of mean, they're all just sort of meaningless for predicting other words. So they all kind of blur stuff together. What that signifies is that these numbers typically do not range between 0. I mean, TF-IDF usually it's like between 0 and, very small, between 0 and 0.2 maybe, because most documents don't overlap that much. And these are just ranging from a much higher range. So maybe you may have 0.6 to 0.8 or something like that is your range. And so you have to just sort of renormalize what you think of in terms of scores. But they're certainly less similar than this of all of these three, right? Yeah. Yeah. Yeah, so the question was, how do we know that it would point to Pittsburgh and not Philadelphia? Or Harrisburg, by the way, right? Because Harrisburg is the capital of Pennsylvania, just like Boston's the capital of Massachusetts. The way those arise is so there's no way that it knows in some sense, right? There's no way that it knows what to do. This is not trained to sort of capture any sort of I don't know what the adjective is for analogical. I don't know if that's an adjective or not, but any sort of analogies. It's not trained to capture these. All that happens is that based upon the data itself, when people talk about Boston and Massachusetts, they use similar other words that maybe relate between Pittsburgh and Pennsylvania. Maybe there's a lot of tech in both those cities compared to Philadelphia. So people frequently say, a tech city like Philadelphia, like Pittsburgh in Philadelphia, or a tech city like Boston in Massachusetts. There are other words that kind of can imply those relationships to make it a higher probability or a higher similarity than other ones. But the short of it is I don't really know what the particulars are, because it's just driven by the data and this completely separate kind of attempt to predict something else entirely. Yeah, so the question was, is it entirely dependent on the backend data? And yes, that's correct. It entirely depends upon the data that's used to create the word vectors. Yeah. Yeah.
So can't you combine both of them and get a better results out of combining both?
The question was, can you combine both of these and get a better result? It really is problem dependent. I mean, for most problems, what you should do is you should try both these things. You can try them together. Oftentimes, you reach points of diminishing returns, right? So there's no advantage using them both over using just one or the other, or the better of the two. So that's going to be entirely problem dependent. Yeah. Yeah. Okay. Yeah, so the question was, can it sentiment? Okay, wait. So those are very different things. So did you mean semantic analysis or sentiment analysis? Okay, so the question is, can this be in sentiment analysis? Sentiment analysis is sort of, determining if something is a positive statement or a negative statement about things. So yes, I mean, a lot of the positive words will cluster together, as will a lot of negative words. And definitely people do use word-to-vec models to sort of, they'll add all the words together that occur as something and say, is that closer to sort of the good words or the bad words? It's not necessarily the only way you can do it. You can do that in a lot of ways by classification and things like this as well. But it's a perfectly reasonable way to use to do sentiment analysis, yeah. And semantic analysis too, by the way, but that's a separate topic. There was a question, one more. Yeah.
Is found by using machine learning techniques of finding the weighted of those and the weights of those by relating to the single word, and then that's how what to make the weight matrix basically formed through machine learning?
The question was, is it all through machine learning? I'll just say yes, it's all just machine learning. Yes. Okay. I mean, so essentially there's a matrix that multiplies this and produces this, and there's another matrix that multiplies these and produces these. And then you have a log penalty that tries to sort of minimize the log likelihood of these things given this one. But we don't know that yet, so we're not going to cover that just yet. Okay, so let's move now to language models and n-grams. So while the bag of words model was sort of surprisingly effective, it's clearly throwing away some amount of data too, right? So for example, if you say something is a boring movie and not great, it's not a great grammatical sentence either, but it's very different from saying great movie and not boring. Again, kind of odd phrasings of these things, but you get the basic idea. But these, of course, have the exact same bag of words representations. These two sentences, they're the same words there. But of course, they mean very different things depending on the ordering of the words. This is the nature of English, right? And that applies to TF, IDF, and word2vec. I mean, you don't gain any benefit from any insight into ordering by using word2vec. It's still just the same. And so to move beyond just sort of this bag of words model, we need to consider something a little bit richer than this, which was going to bring us into the domain of language models. Now, we haven't, I'm going to have a caveat here. So we haven't actually had our lecture on probability yet. So I'm going to write some things here that hopefully are sort of understandable. We're not going to cover anything other than just counts, literally, and probability. That's the extent of probability here. But I'm going to use notation like the probability of something given other things. And I will try to define it, but hopefully, if you haven't seen it before, you can still kind of follow along the basic ideas, and we'll kind of we'll return to probability in a later lecture. And if this currently seems odd, then hopefully after we do that, it'll be more intuitive then. So what a language model does is it predicts the probability of the next word, essentially in a document, given all the words that occurred before it. So it predicts the probability of word I given words 1 through words I minus 1. And so this is actually, while it seems hard, right, there's some sense in which we kind of know that in a sentence that there's a very limited number out of all the possible words of words that kind of happen next, right? So, and that even includes grammatically correct words. So if you have a sentence like data science is the study and practice of how we can extract insight and knowledge from large amounts of something, it's probably going to be, the next word is probably much more likely to be data than it is to be hot dogs. That wouldn't really make any sense, even though it's grammatically correct, right? You wouldn't even think that would be the next word you should really use there. This was before the hot dog app became a craze. I wrote this slides before the hot dog app became a craze in AI. So take that for what it's worth. Okay, so this is the goal of language models, is to sort of give a distribution over the next possible word, given everything that's happened up until now. Okay. Now the trouble here is that building a model that captures the actual sort of inherent probabilities of real language we are still not that close to there. We're getting better, certainly with some of these deep learning based language models certainly seem to be getting a little bit better, and they can produce convincingly accurate text, but it's still a distant goal to really understand, the real kind of meaningful semantics of language. And so instead, we're going to make simplifying assumptions about how to sort of approximate this that generate tractable models that are still surprisingly useful in practice. And kind of the workhorse here, which again has been definitely superseded by more complex algorithms, but it was still, potentially a very strong baseline in some cases, is the n-gram model. And the idea here is very simple. It's that we're going to model the probability of a word I based upon only the n minus 1 words that precede it. So if we have a 2-gram model, we model a probability of a word, or a bigram, that one has a special name. We model each word given only the probability of the words that happened right before it. And so what this does is this puts kind of a hard limit on the context we can use to predict the next word. And it makes the modeling, by doing that, it makes the modeling much more tractable. And so, for example, you would only consider, rather than this entire sentence, right? You would only consider the recent context when predicting the next word. So, if, for example, in a 4-gram model, you would predict large amounts of something. Could it be large amounts of data or large amounts of hot dogs? Now, of course, those phrases by themselves actually make a lot more sense. You might, this one's still probably a little bit less likely than this one. But they at least make much more sense. Whereas when you include the whole context, clearly the second one does not make any sense. So again, we're throwing out a lot of real knowledge here. But we're doing that, we're making that sacrifice to gain tractability of the models. Okay, so now let me actually just sort of, for those that sort of are looking at this notation and not being quite clear on what I mean by this, let me sort of explain this and sort of emphasize that all I'm talking about here is just counting, right? So the model I'm going to use is that the probability of some word I, and really what I mean by this is I'm going to compute a probability for every possible word that could happen. I can compute that probability of that word. So the probability of word I, given word sort of I minus n plus 1 to word I minus 1. This is going to be equal to, I can write it kind of both ways. I'm writing it down by hand, so I'll write it this way. This is just equal to the number of times in my data set I've seen this whole sequence. I've seen basically word I minus n plus 1 all the way to word I. Number of times I've seen that whole phrase. So basically the number of times I've seen, large amounts of data divided by the number of times I've seen word I minus n plus 1 to I minus 1. In other words, the number of times I've seen the preceding phrase. So if I want to compute the probability of data given the past of large amounts of, I just compute the number of times I've seen the phrase large amounts of, and then the number of times I've seen the phrase large amounts of data, and divide one by the other. That's the extent of probability we're talking about here. Yeah?
Does this work for weather predictions too?
Would it work for weather predictions too? Weather's so I mean, this kind of models can work for weather predictions, but this is kind of a different thing because weather is a continuous quantity that has trends and stuff like this that is a little bit more has a little bit more dynamics to it than just words. Whereas these are all discrete things, so you can just count. Weather, you might have a temperature that is a little bit in a gap you haven't quite seen before, so it doesn't really make sense. You can discretize it and sort of approximate it, but yeah. Okay, so that's all I mean by probabilities here. It's just counting. So hopefully it's not too hard, the kind of probabilities that we're going to deal with here. All right, so for example, the goal of this lecture is to explain the basics of free text processing. So under a 2-gram model, what is the probability of word I for all possible words that could be, given the fact that the previous word is of? Asking a question now. It's not a poll question, but asking it to the audience. Want to say? Yeah. Is what goal?
So on the problem, I was thinking, since you previously see that the previous word is word I minus 1 is goal.
But I'm saying word I minus 1 here is of. I'm saying what's the probability of the next word given word I minus 1 is of? Okay, yeah, so what are they? What is it? Sorry. This and free? Okay, so I mean, what does that mean? What's the probability of those two? Okay. So you're saying the probability of word I being equal to free given word I minus 1 equals of. Is what?
It exists just once in the sentence. It exists
Yeah. So what's the probability in this case? 1 over 2. Has it's occurred? Yeah. So you've seen the word of twice. One time it was free afterwards. The probability of free, given the previous word being of, is 1/2. What's the probability? What's the other one of relevance here? This. Yeah. Oh, I'm sorry. I've been writing this whole time. I didn't realize. Okay. Sorry, I was just taking notes here, apparently. So the probability of the word I being equal to free is, given the word I minus 1 equals of, is just 1/2. Similarly, this, what's this probability? What is it? 1/2, yeah. Okay, and what's the probability of this being, let's see, what else do we have? Lecture. What's this probability? 0. Right? If I get 0 for every other word besides this and free. Okay, so those are the probabilities. And it's just counting, right? That's the way you compute probabilities in these models, is you just count the number of times you've seen the preceding phrase, and the number of times you've seen the entire phrase, and just divide the former by the latter by the former. Okay, so that's the extent of probability we deal with here. Now, one thing that is the case is this seems a little bit strict, right? Because do we really want to say that there's 0 probability of some other word occurring after of? I mean, 0 is really low, right? Like it can never happen then. If you predict something, you say, for example, 0 probability, and it does happen, you're infinitely wrong, I guess, in some way, right? So a common way to kind of get around this kind of harshness here is something called Laplace smoothing. So the idea here is that you do counting as normal, but you also add a small little factor alpha to every numerator. And then, of course, to make them all probabilities, you would add alpha times d, where d is the number of total words in your vocabulary, to the denominator. Right? And this would essentially, make this basically, in our case here, in practice this would be something like, this would now be, 1/2, it'd be minus 0.001. This would be, minus 0.0. Actually, it's not that. It's those don't add to the right thing. So minus something here, whatever. And this would be, 0.001, etc., such that these things all add into 1. But basically, it allows for some violation of what you've seen before, in the hope of, catching the rare case or the realistic case that you're not going to have seen everything in your data set already. It's also possible to have kind of backoffs that use lower degree. And so if you've seen, if you haven't seen a whole history of a certain n-gram, so you haven't seen 3 words in succession, but you've seen the last 2, maybe you just back off to like the 2, I guess the trigram model to predict the next one. So the previous 2 to predict the next one, instead of using the 3 to predict the next one. And then if that doesn't exist, you back off to just 1 to predict the next one. If that doesn't exist, you just use like the nominal frequencies of words occurring. Right? So there's also things like that, but there are different sort of things you can do here to kind of smooth this probability away from the harsh case. Okay. Now the question is, how do we pick n? Right? How do we pick the size of our context? I mean, I sort of said before that really, in some sense, we want a big context, right? Because the data science example, when you talked about a sentence like that I described with, data science is this and this, and it implied what that next word could be. That sort of implies we want a big history, right? To keep a large context, keep kind of as informed as we can about the next word. But it's also the case that the more context we have, we need more and more samples, right? Because the chance of any particular exact phrase occurring, and remember, we're only counting exact phrases occurring here. The chance of that happening is less and less the bigger your history is. Right? So typically the correct choice is to use some measure, like the right way of doing it is to use some measure of what's called sort of cross-validation or holdout accuracy. We'll get to that much more when we talk about machine learning. But in practice, basically the choice is, if you have a big data set, you use n equals 3. And if your data set is not big, you use n equals 2. So if it's small, you predict just from the previous word. If it's big, you predict from the previous 2 words. In reality, you have to have a really big data set before even going beyond that really helps you a lot. Maybe, I mean, you can. There's plenty of, definitely that billion word thing Google was doing. 100 billion was definitely doable there. But it's still, not, for most data sets you'll encounter, trigrams and bigrams are kind of fine. So here's some examples, actually. So here is and you're actually going to do some language modeling on the next, I think the 688 question in the next homework. Here are some examples. So I trained, this is sort of one of the standard things you do with n-gram models, is you train a Shakespeare generator. So there's collections out there. They aren't that big. They contain all the works of Shakespeare. I think I actually used one in one of the, I think in one of the first lectures, I think, on something I used one of those. Maybe parsing, I used the Shakespeare. But now we're going to use it to actually model the language of Shakespeare. So what I'm going to do is I'm going to take the entire text of Shakespeare's plays, and I'm going to create 1 gram, i.e. I'm just sampling random words from Shakespeare. Bigram, I'm n equals 2. I'm sampling the next word based upon only the previous word. And then this model, I'm sampling this word based upon the previous 2. Now, it's important what I mean by that. So what I'm doing is I'm sampling here. So what I'm doing is I'm basically computing, given the past history. If I don't have any history, I just use the first model. If I have only one, I use this one. But given this one, these 2 words, and actually a comma is also considered a word here. So given these 2 past words, there's some set of all possible words that Shakespeare used after believe, comma. Right? So if you look at all of Shakespeare, he used they sometimes. He probably used some other words sometimes. He probably used he, she, these things, right? So I'm going to take those probabilities. I'm going to sample from that distribution, right? So those are just a distribution over just different words. I'm just going to draw a random sample from that, and I'm going to use that to generate my next word. Then I'm going to move forward. I'm going to use these 2 words, and then draw a sample of the next word. So I'm sampling, actually. I'm not looking at any real text here. What I'm doing is I'm first building my model just by count, and then I'm just sampling based upon the probabilities implied by those counts. And pretty quickly, usually with about n equals 3, you get sort of very funny text because it's surprisingly understandable. And so, I think at least there are certain things, right, where I would not know if it's real Shakespeare or not, because it's hard to read Shakespeare enough as it is, and so maybe it's just Shakespeare being Shakespeare, or maybe it's actually just the model saying weird things. So when you get to n equals 3, believe they all confess that you withhold his levied host, having bought the fatal bowels of the Pope. I mean, it makes no sense at all, but it's actually kind of funny, right? It's actually kind of grammar. I mean, there's no grammar here or anything like that, but it actually is there. Now, in data science, oftentimes you don't really generate stuff in data science. This is more like a cute little toy you can do. But these models actually are very valuable for data science because they do let you sort of determine kind of what is the most, what are the probabilities of new documents given some old documents, and how well do they match up with kind of the general text seen in a previous document. One quick note here, and that is that if we go really high, so say we take size 7 n-grams, you start getting things like this. And actually, this is a little, so this is maybe not perfect here, but this is actually looking a whole lot like Shakespeare at this point. They're actually, this actually becomes, kind of grammatical. Seems kind of, looks just like Shakespeare. And that's actually because it is Shakespeare. So what's happening here when you have a very long history is that in your training set, there's only going to be one case that you've ever seen that succession of 6 previous words. There's only one word that ever comes after that in Shakespeare. And of course, the number of possible combinations goes up exponentially with a really high exponent too, because each one is different words you can use, right? So it goes up, the number of possible contexts, histories, goes up exponentially. So the chance of them, you finding more than one time the exact same context just keeps going down and down. And so what sort of happens is that you basically just pick, if you don't have, the Laplace smoothing at least, if you have that, you just kind of sample randomly. But if you don't have Laplace smoothing, you just kind of latch onto some paragraph in Shakespeare and just kind of march along just sampling from that exactly. Right? So there's definitely a limit here. And we'll talk very briefly about the problem with this in a second. But I mean, it isn't too impressive that you can kind of look up Shakespeare's text and just repeat it. What's actually kind of interesting is that you can, when you don't have such a long history, you can generate things and model things that actually are, look like actual text. Okay, so this is going to be kind of actually now a kind of hinting forward at some things we're going to talk about in much more detail when we talk about machine learning, but I think it's sort of good to mention it here. Again, in data science, you don't really care about generating Shakespeare text, right? But you might care about analyzing a new text and saying, how much like Shakespeare is this? Or maybe I have a bunch of different texts and I want to know, and this is actually what you will do in your homework, you have a bunch of different texts with known authors, and you want to know, you have some new text with an unknown author, and you want to predict who's the author of that new unknown text. Right, that's actually a pretty, you can imagine that task coming up a fair amount. Now, the way you usually evaluate how well a model is fitting a certain document is by something called perplexity. And what this is that this is actually 1 over the probability of the entire sequence to the 1 over n. So basically, the probability of the entire sequence is going to be very small, because that's, every time you see a new word, your probability just keeps going down and down and down. And so to sort of get something regularized, and you take 1 over that because you want higher probabilities to be better, or higher perplexities to be, lower perplexities to be better. Higher probabilities mean lower perplexity. And you kind of scale it by taking the 1 over nth root in order to get something a reasonable range still. So just to be clear, the way you compute the probability of the entire document is you just compute the probabilities 1 at a time. So for all I from n to the total length of the document, you compute the probability of that word given the previous words before it. So I just do that for all the words in my document. I multiply them all together, and that gives me the perplexity. I mean, when I plug in that formula. Now, actually, what you really do is you compute the log perplexity first by computing the log of this term. This term, these are all less than 1 or between 0 and 1, right? So if you multiply them all together, they get really small. What you actually do is you take the log of these things and you add them up, and then you take 2 to the log 2 of this thing, and that's how you really compute the perplexity in practice. Yeah.
So why does the product go from n to n, like small n?
So the question was, why does the product go from small n to big N? Big N is the number of total words in the document, right? And in order to predict the ith word, you have to have at least I minus 1 previous words before it. So word n is the first word where you have enough context to predict anything. All right, so I'm just going to start at the nth word and then predict every word after that until the very end of the document. Okay, and now just a hint of sort of these notions from machine learning of overfitting and underfitting, this kind of stuff, which we will get into much more later in the class. I want to point out that perplexity will always decrease for higher n on the data set you train the model on, right? Because the more you can kind of just, predict exactly what's going to happen next, the better your perplexity is, the lower your perplexity is. Lower perplexity is better. So it'll keep getting lower and lower, the more sort of certain you are. And as I showed before, when n is 7, you're really certain because you've only seen that thing once before. You know exactly what's coming next. Again, on the data you trained it on. But the important thing, of course, is that if I evaluate it on new data, that doesn't happen at all. So on new data, I think this is the Shakespeare model here. Once I actually go to even n equals 3, it looks a little okay, but actually in terms of predicting what is going to happen in the model, it's quite bad. I think this is Shakespeare. I should actually verify that, but this is some model I trained. 2 actually is an improvement from 1, so just predicting the raw counts is in fact not great. This is a log scale, so it's sort of hard to see big differences here, but this is actually is an improvement there. But after 2, you just sort of start getting worse and worse. And actually, because essentially what happens is I haven't seen anything before, right? I'm going to find some context I've never ever seen before, and the only reason actually why it's not infinite is that I use Laplace smoothing. so I can kind of be okay in terms of getting some reasonable amounts of probabilities, or not hurting myself too much. But basically, once I am at 10, I have no idea what's coming next because I've never seen anything in this new document before. So this is sort of the big difference here between what's called training set and validation set performance. This is kind of a validation set. It's a new document I have not seen before, and when I want to analyze how well I do on that, it's kind of what really matters. And it's not always easy to understand that from just training itself. Okay, and again, this is a preview of the underfitting and model selection stuff, which we're going to talk about a lot more in machine learning. So you might want to select a model of n equals 2 based upon this. And so we'll talk about kind of more rigorous ways to go about selecting different model parameters. Okay, so with that, I want to finish in the next 15 minutes by just talking about some code and some libraries you can use to do some of these things. There's been two libraries I'm going to talk about for this: NLTK, which stands for the Natural Language Toolkit library for Python, and also a library called GenSim, which has some nice things like word-to-vec models built into it. So NLTK is kind of the standard Python library for handling text and natural language data. Having said that, it's not actually that great. It's this huge library that has tons of different routines and modules, and it's really unclear kind of what the best ones are in a lot of cases, or which one you should even be using, or you might have to download like external data to even use it oftentimes. But it is still kind of the standard, and so a lot of tools will use NLTK for things like tagging sentences or parsing them, and et cetera. And actually does not always have sort of the more basic tools from language. It really is more geared towards natural language processing. But it's so common, and there are some sort of nice utilities it has that it's worth sort of knowing it, and you will use it a little bit on your homework. However, if you want to, so it doesn't, it also omits some things, like there's no TF-IDF. I guess they just didn't want that. They have everything else, but they didn't really want that. I guess it's not quite, this sort of comes from more like the information retrieval literature, so it's maybe a little bit different than they think. There was an Ngram language model, but they removed it because it had too many bugs in it or something like that. I mean, I don't understand why, because it's the simplest thing you could possibly write, but yeah, there were some bugs in it or something like that, and so they removed it. And so if you do want sort of a more kind of, I guess, like well-contained library, I recommend checking out things like Spacy. This is a really nice one. And Core NLP is actually, it's from a group at Stanford doing NLP, and it's actually quite advanced in terms of they have really powerful models here. But this one also has powerful models and a little bit more user-friendly. So we're going to use this one. It is kind of the standard still, maybe becoming less of a standard as time goes on. But you still see it a lot. So let's see a few things you can do with NLTK. So one thing you have to do is actually, the first time you run it, you have to run also, you import NLTK, you install it with pip or whatever, or with Conda. But then you also have to run NLTK.download. It has its own like package manager internally to NLTK that determines what corpora you have and what extensions you have and this kind of stuff. So you have to run that once. I'm commenting it out here though. So now it has things like being able to tokenize words. So the goal of the lecture isn't to explain complex free text processing. If you tokenize this, it sort of breaks up into words. One thing you'll notice though is it takes things like isn't, and we'll separate them into is and not, essentially. So it will break down certain stems into sort of their constituent parts in a way that's helpful for comparing between different documents, right? Because if you have something like, it didn't do it here. I think sometimes there are other routines that will do things like process and then ing to that too. But basically, we'll do some very simple processing of your data to remove kind of incidental parts that make things different. You also tag parts of speech. So you can say, is this a noun? I don't even know all the types of words that there are, types of things. I think this is a verb. This is another noun. Know those. This is an adjective. I forget what all the other things are called. It's been a long time since I studied grammar. But you can basically get parts of speech for the different words in your sentence. Again, those are guesses. It's not definite because there's no unambiguous way to know what things parse speech are in the English language, but you can typically do a pretty good job with that, and it's using a pretty good parser to sort of determine what different parts of speech are. You can also do things like remove stop words automatically. So you can take, you know, they have basically built-in words of stop words for English, and you can basically, oops, I haven't Python 3'd this code yet for this one, but you can basically take your list of tokens and say remove them if they're in the stop words. So that will, you know, we talked about doing that. We didn't actually ever do it, and that did mess things up, like with the high similarity between, you know, the database stuff and Pittsburgh, just because he had the is a, something like that. So you can actually use this to remove stop words. And it has a, you know, a nice list of stop words. They're sort of standardly accepted in English. And you can also do things like n-grams. So it has an n-grams thing that can generate, basically take the tokens and generate n-grams of size, whatever you want, and iterate over those. Now, you actually could do the same thing in this line of Python 2. So it's not necessarily worth using NLTK for this, but it's there if you want to use it. Okay, next up, in the 10 minutes or so we have left, I'll talk just about any questions so far about NLTK? Okay, next up is, I might actually finish early today. The GenSim library. GenSim library describes itself as a topic modeling library, and it does have topic modeling things too, but it has also done a fair amount of sort of nice routines built in as well. So GenSim has actually one of the nicest Word2Vec, sort of public Word2Vec implementations for Python that I'm aware of. It has actually C functions for the training process, so you can actually train your own models, not just use pre-trained ones, but you can also, of course, load in some pre-trained ones. It does not include the pre-trained models themselves with it, so you have to go out and find a pre-trained model. But those two links that I had before give some instances of pre-trained models. It does have code to create TF-IDF vectors, exactly how we saw in class. Scikit-learn, which is a machine learning library, also has code to generate TF-IDF vectors, but they use a different definition of inverse document frequency than the one everyone uses and the ones we used here. I don't know why. So I think this is a little bit cleaner. You can just test this and see you get the exact same results that we had earlier in the slides. And then it also includes topic modeling algorithms like latent to reach late allocation and some others. Those we may get to if we have time in later lectures, but that's not certain yet. They essentially are ways of combining similar topics together. Actually not that dissimilar from Word2Vec, but they're using very, very different techniques. And actually, you know, I shouldn't say those things are similar, because they're actually accomplishing very different goals. This is much more if you have a whole collection of documents, LDA that is. If I have a whole collection of documents, how can I assign different documents to different topics? And different documents, different proportions of topics. It's also fairly interoperable with the corpus objects from NLTK. So if I take a corpus from NLTK, I can run all my GenSim routines on that. Now, keep in mind that you typically do not want to train your own Word2Vec models. That typically is quite slow, and you need a really big data set more than anything else. So you really need to either train all of Wikipedia, but you shouldn't do that because there's already pre-trained things on Wikipedia, or you need to have some of your own data set that is just really massive, that has the billions of words we're talking about to train these things well. You can't take a few free text comment fields in some database and hope to build a new model from that. So I typically will just use the built-in or some pre-trained models for all Word2Vec stuff, even with GenSim. So just quickly, let's see a few examples of this. So this is how you set up a corpus in GenSim. So I'm going to import GenSim as GS. Here are my 3 documents. This I'm going to do a little bit more manually now than you could do with NLTK, but I'm just going to do it kind of manually here. I could remove stop words and stuff with NLTK too, but I'm not going to do that. I'm just going to take my words, and the words are just going to be the split, d.split for d looping over the documents. So I'm going to take each document, split it by, in this case, by the spaces, And so I have separate words now. I'm going to form a dictionary, which is the unique number of words there. And then I'm going to form a corpus, which is dictionary converting it from a doc to a bag of words for that word for all the things in words. So don't worry about it too much. Basically, this is a way of converting. This is just sort of how you set up a corpus in GenSim, and you can look. You can run this code yourself. When the notes are up, this will all be there. You can see what sort of the value of corpus is. It's basically a list of kind of tuples of, this document contains this term, this document contains this term, et cetera. And that's just how you represent corpora in GenSim. Once you have a corpus, I can create a TF-IDF model. And I can do things like create the X matrix by creating a corpus to compressed sparse column format of my corpus with TF-IDF scores. So this is a sparse matrix with the TF-IDF scores of the words in this document. So it creates that X matrix we talked about at the very beginning or the end of last lecture, and returns it natively as a compressed sparse column matrix. Again, for things like word frequencies, you really want to use a sparse matrix to represent those. Not, by the way, for word vectors, because those are dense. But for these word frequencies where you use one-hot encodings, you want to use a sparse matrix. I can also use this, again, this is just sort of notation here, but I can create a class that will compute similarities between them. Then I can compute all similarities between them. So this will actually give you exactly a matrix, just like the one I showed on the first slide or the middle slides between these different documents. Finally, I can also do things like load pre-trained Word2Vec models. This is just the call for doing that. So my pre-trained model is a file called deps.words. That's from one of those, the second set of pre-trained models I mentioned, because the first one actually won't run on my computer. My computer is actually not big enough to run the Google 300 dimensional word vectors. So be careful if you have a computer that isn't brand new. Again, 16 gigs of RAM is what you need. I can look up the word vector for Pittsburgh. I can do things like find the most similar vectors to Pittsburgh, and I can do things by this analogies by vector addition. So I can find the similar ones to Boston, Massachusetts plus Pennsylvania. I can find the most similar ones to that as well. Now, there are also routines for doing all this sort of just passing in individual things rather than manipulating the vectors and then doing it, but this is more explicit, so I kind of prefer to do it this way. And then finally, if I want to create a Word2Vec document representation, I can take I can sum over all the word vectors for the words in the document, and I can do this for all the documents in my corpus, and then create an array of this whole thing. This is now an array of X, where I'm using sums of Word2Vec based document bag of words. And I can do things, and I'm now going to normalize the rows, and I can print the similarities there. So this would be exactly that second M matrix that you saw there that had a higher similarity between the first two, even though there was no overlap in words. So that's it. That's all we're going to talk for now about free text processing. Hopefully gives you some idea of the different techniques and the kind of different powerful methods we have in data science to handle free text.